All right, let's dive in. We're about to go on a quest to understand this secret mathematical language. It's a language that, believe it or not, describes the very structure of the world around us, from the tiniest virus to the biggest crystal.
So, to kick things off, I've got a question for you. What in the world is the hidden link between a virus and a diamond? I mean, they couldn't seem more different, right? One's a biological particle, the other's a crystal. But they share something incredibly deep.
Well, the answer is symmetry. And it's not just about things looking pretty. There's a whole secret language mathematicians created to describe it, to really pin it down with absolute precision. It's called group theory, and it's basically a way of cataloging every single move you could make to an object that leaves it looking exactly the same.
Okay, so how do we start to learn this language?
Well, the good news is we don't need to jump into anything super complicated. We can start with something you see every day, a simple shape, and just figure out its rules.
Let's take a square, just a plain old square. Now, think about this. How many different ways can you pick it up, move it around, and put it back down so it looks completely unchanged? You could rotate it 90 degrees, right? Or 180, or 270. You could also flip it over, either horizontally or vertically, and that's it. The really important thing here is that there's a limited, specific set of these moves. Each one is what we call a structure-preserving transformation.
And that complete collection of moves, that whole set, that's what mathematicians call a finite group. It's the entire toolkit of transformations for a given object. For our square, the elements of the group are just those rotations and flips, and the operation is what happens when you do one move and then another.
Okay, so we've got the basics down with a square. But this idea, this concept of a symmetry group goes way, way beyond simple shapes. It applies to, well, just about everything. In fact, there's a whole zoo of different kinds of finite groups out there.
Take permutation groups, for example. That's really just the math of shuffling things. Think about a deck of cards. A permutation group describes every single possible order you could arrange those 52 cards in, and that number, 52 factorial, it's just mind-bogglingly huge. Then you've got something much simpler, cyclic groups. These are kind of like a clock. Every move is just one tick forward, and if you keep doing it, you eventually end up right back where you started. Simple, predictable, cyclic.
So this huge variety, it brings up a really big question. I mean, if you have all these different types of groups, from the super simple clock-like ones to the insanely complex shuffling ones, can you break them down? Are there fundamental building blocks, some kind of mathematical atoms that everything else is made of?
And the answer is a huge, resounding yes. It turns out there are. It's an amazing parallel to something we're all familiar with. You know how any whole number can be broken down into a unique set of prime numbers, right? Well, it's the same idea here. Every single finite group, no matter how complicated, can be built from a set of basic, indivisible groups called simple groups. These really are the fundamental atoms of symmetry.
And look, this isn't just me trying to make it sound simple. This analogy, this idea of atoms, is the core concept that launched one of the most incredible, most ambitious projects in the entire history of mathematics. It was a quest to find and to classify every single one of these fundamental building blocks.
So, what did this quest actually look like? Well, it was absolutely monumental. The search for all the simple groups resulted in a proof so gigantic, so sprawling, that people just started calling it the enormous theorem. And trust me, it earned the name.
And get this wasn't the work of some lone genius scribbling in an attic. No way. This was a massive global collaboration. Over 100 mathematicians were involved, each contributing crucial pieces to this gigantic puzzle.
And it wasn't quick either. This was a multi-generational quest. It took almost 50 years to complete. Think about that. It started back in 1955 and wasn't officially finished until 2004. Entire careers were spent working on this thing.
So, the final result, the proof itself, it's spread across hundreds of different journal articles, and if you printed it all out and stacked it up, it would be more than 10,000 pages long. It's seriously one of the longest and most ridiculously complex proofs ever created by humanity.
So, after all that work, after 100 mathematicians and 50 years and 10,000 pages, what did they find? They found everything. Seriously, they created a complete, exhaustive list of every single fundamental component of symmetry. It's like a periodic table, but for groups. And here it is, the whole shebang. It turns out most of these simple groups fit into a few big, predictable families.
You've got your cyclic groups and alternating groups, plus 16 whole families of what are called groups of Lie type. Those are related to smooth, continuous symmetries. But then you get the weirdos. There are 26 of them. They're called the sporadic groups. These guys don't fit into any neat family. They're just there. Strange, beautiful exceptions to all the rules, each one discovered as its own unique mathematical creature.
Now you might be sitting there thinking, okay, that's cool, but why? Why go to all that trouble? A 10,000-page proof just to make a list. Couldn't they have just found them one by one as they needed them?
Well, here's why. The number of possible groups for a given size doesn't just grow, it explodes. It's exponential. For a group of size 4, there are only 2 possibilities. But as you can see, by the time you get to just size 16, there are already 14. This number just goes through the roof, and without a complete map, without the classification theorem, trying to navigate that complexity would be totally impossible. You'd be lost.
And here's the most crucial point of all. This was not just some abstract game for mathematicians. This completed map of symmetry has profound, real-world consequences. It's a fundamental tool used in chemistry to understand how molecules are built. It's used in crystallography to describe how minerals form those perfect, beautiful lattices. It's even used in particle physics to classify the fundamental forces of our universe.
Which brings us to one last big thought. We've done it. We've found the complete alphabet for the language of finite symmetry. The list is finished. And that just makes you wonder, what other secret mathematical languages are still out there, hiding in the universe? What other structures with their own alphabets and their own enormous theorems are just waiting for us to discover them?